Hello everyone. So we're Team H and welcome to our Spring Validation demonstration. I'll start the presentation. So we have three demonstrations lined up. The first demonstration is about the image processing system, and the goal over there is to show the model that was trained on the data we captured and show its performance. The second demonstration is about trajectory processing. So the goal is to have some kind of integration of the detection and the tracking systems. The third demonstration is the simulation runner, which runs the models on multiple agents in the simulator, which is our end goal. So let's get started with the demonstration on the detection. This is from the SVD one pager that we shared. The process is basically we have the video streams and we'll be running the detector model on it. And the metrics that I mentioned, precision and recall, will be calculated against the ground truth. I'll go into the metrics after this. The data set that we captured is around 14 videos of 2 minutes from Carla. And at 2 frames per second, we used those annotations and got around 3,360 images. We split them randomly into train and test images. So we have 2,600 training set images in the training set and 672 images in the test set. We trained a faster CNN model, which was pre-trained on Coco, and we fine-tuned it with our data. And the metrics that we measured are precision and recall. So precision is out of all the predictions that you say, the ratio of the correct true predictions against the false predictions. So we achieved 84.99 on. So all these metrics are on the 672 images of the test set. We use that as the base for our calculation because it's a general randomized extracted data. So we got 84.99% precision and 94.05% recall. So again, I'll just go over precision and recall again. In simplified terms, precision is if the model said there are 10 objects, at 84.99 precision, we have 8.4 objects correct and in terms of recall, if there were 20 objects in the real world and the model has 94.05 recall, it means that we have 9.4 into 2, which is around 18.8 correct. So the model is able to extract 18.8 correct vehicles from the real world. So the thresholds that we used over here are the confidence threshold first. The confidence threshold is the first gate. If the model, so with every box that the model gives, we have a threshold that comes. If that threshold confidence of the threshold confidence is below 70%, we just ignore the detection. We don't consider it at all. The second gate is the intersection over union overlap, which is used to identify whether a box that was predicted by the model is a true box or a false box. So if the overlap is 50%, which is our current threshold, we consider it to be true. So these two are the tunable parameters that you will see. I'll just go through the first demonstration where we are running this on the video. So yeah. Yeah, so we are visualizing precision recall in real time. So this is an accumulated matrix. So now the precision of 79% you can see is from all frames from now to the previous value. We can in the terminal we can see the current status. Like we have a 300 frame video. So over time the values of precision recall are being calculated again. The gray boxes that you see behind the colored boxes are actually the ground truth. And all the colored boxes with the text are the predictions of the model. So in some cases, far away on the right side, if you see, at times the prediction fails, but the ground truth is there. That is where our precision recall metrics are being hit. So this is a curve that we use to estimate our precision recall threshold. So at a 70% threshold, you can see we are at a precision of around 85% and recall of 90% plus. This is for this particular use case, of course, but in general, this is a good way for us to get a good threshold. So at 90% threshold, you can see there is a high precision, but because your gate is so high, the recall is lower. And if you keep the threshold very low, you end up detecting more of the real world objects, but then your precision becomes low because there is a lot of noise. So yeah, we would now have some ability to tune these parameters as the video is just ending. So yeah, you can see that there is some difference in the general IOU of the boxes. So in terms of tunability, we have tunability of the confidence threshold and the IOU threshold. We can increase either one of them and get an increased precision because we ensure the gate is higher. And if we decrease them, the recall increases basically. So anyone from the audience, like in general.
So the confidence threshold is the detection confidence threshold?
Yes, yes. It's a combination of the classification and detection. So it's both. So would you, like, what could I can try anything if you would want.
Let's move it up to 85%. How's that?
Sure. So over here you saw that we ended at around 85 precision and 95 recall. Yeah, I'll just quit this. With the new values, let's see what we get. Yeah, so recall is lower for sure in the beginning.
The recall was over 95 before, was it?
Recall previously was around 95% that we were getting, and precision was 85 in the end. But we can see the precision increasing as we get more and more detection. So yeah, this is an indication of where we are moving. Basically, we're moving up the curve towards higher precision.
Mm-hmm.
And yeah, so we are somewhere here right now, 85%.
Mm-hmm.
So in the end, yes, we should have a lower recall and a higher precision. Like we had 85, so hopefully it should be higher.
Okay, that looks good. Did you guys want to try the other direction, or should we go on? I don't want to take time away from the other. Maybe we come back.
Yeah, we can move on to the next demonstration as well. So yeah, next demonstration is we have Mandeep ready for the next demonstration. Mandeep, I guess your mic is muted.
Yeah, sorry. Thanks. So this will be the demonstration of our tracking algorithm. So if the procedure would be like that, the video that we will capture from the data capture system, we will be running our detection model on top of that, and then that we will be using those bounding boxes and transforming them into the bird's eye view, and then we will be tracking different agents in the bird's eye view. The validation criteria for this will be MOT A and MOT P. So these are the accuracy and precision in terms of multi-object tracking, and we propose that it should be at least 40%. I'll quickly go over what multi-object accuracy in terms of tracking means. So it is basically, for example, you have three proposed hypotheses which are represented by these dotted lines, and there are three ground truths which are represented by these ovals. So the accuracy is in terms of how correctly we are able to associate the ground truth and the proposed hypothesis. So in this case, you can see that we were able to correctly, in this particular case, two proposed hypotheses are being able to match to the ground truth, whereas one is left. So this will be counted as a false positive and a miss. So basically your accuracy tells you the number of false positives and the misses and the mismatches. Whereas the multi-object precision is in terms of how far my proposed hypothesis is from the ground truth. So as you can see, like it will calculate the Euclidean distance between the two trajectories at every time step, and it will keep accumulating it to compute the precision. So yeah, so currently we are able to achieve pretty good accuracy and precision, and this was computed over 10 random scenarios and averaged over it. So moving on, I'll now show. So before beginning the demo, I just wanted to hint to what we will be showing. So in this particular scenario, on the left hand side is the bird, is the camera view, a captured video. We are running a detection model on the left hand side, and on the right hand side is the bird's eye view, where so this is some scenario that has been captured, and the right hand side you can see the mod A and mod P. This is what we will be seeing in the demo as well. So now up to for the tunability, one sec. Like the option here is that we would want you guys to choose any random traffic location that we have been pre-captured. The reason that we had to pre-capture these locations was because so the input to our system is a video, and to get the quantitative metrics we will need to have a ground truth. And so there have been some scenarios where we have just randomly spawned a traffic light and captured the data and computed its ground truth, and now we will be able to show the real-time metrics. So as you can see, like as I showed in the map, so these are the particular intersections that we were able to capture, and I would want you to choose any scenario that you would want to see, basically on the, yeah, like which one seems more interesting to see?
Demi or Hayes, you want to pick one?
65, I would say, because it has this weird
Yeah, sure.
lane going on.
Okay, cool.
Are these different from the 10 scenarios that you averaged across?
Yes. So these were like that was, so we calculated like around 15 videos, and then we just separated 10 those and 5 of these.
Okay.
So is this, Mandeep, is this, we're going to see one agent basically, or you can do this on multiple agents, multiple cars basically?
This will be, yeah, it will be on multiple cars for sure. Like, I didn't get what exactly, like, can you repeat?
Yeah, I was going to say in what we're going to see next, we're going to be tracking one car. We're going to be looking at this hypothesis you've described for one car.
No. For all the cars that will be in the intersection.
Ah, okay. Got it.
So just to be clear, you guys are performing the tracking in the bird's eye view and using the front view just to make the detections and associate the tracks, right?
Yeah, just for the video.
Associations are made in the bird's eye view. So like associations are made both in the camera view and the bird's eye view. And in the camera view, we have S.T.A.R.S as a tracker, which is giving this preliminary tracking information, like vehicle 1, vehicle 2. These are the left you see are from the S.T.A.R.S, and on the right is our own tracker in the bird's eye view, which takes the prior information from S.T.A.R.S and then computes again the associations.
Okay.
If there's any switching in the left hand side, which you'll find sometimes the S.T.A.R.S tends to switch, especially when the vehicles are far away, then on the right hand side, a tracker is able to rectify those.
Yeah. So and now moving on, I'll just explain what this black boundary is. So this is like a region of interest. So we do not want to predict the locations of the agents which are too far from the intersection, because that will also lead to more number of false positives and mismatches. And also we do not really care like what is happening too far. And so, and the black you can see is the ground truth that was captured from the Carla, and the color trajectories are our proposed hypothesis, and you can see the real-time metrics. Yeah.
So the one we see at the bottom, is it vehicle 8 that has just arrived? Or is it?
Yes, it was vehicle 3. It was coming from the forward.
Vehicle, or is it vehicle 3, I guess? Sorry.
Yes, it was vehicle 3.
Vehicle 3, yeah, it's from the other side. Yeah, it's like the rotating the map is like 90 degrees.
Oh yeah. Yes.
Yeah.
Yeah, so this particular video is over, and you can see in the end, like we were proposing 40%, we are getting 80, around 80% in this, the accuracy. And if you would like me to try any other scenario as well, like we can go, where is that presentation?
How did you pick 40% at the beginning? Was there a reasoning or just seemed like
So initially when we were, this area was new to us, and we didn't know initially like what would be a good metric. So we tried to undercommit, but now we see like it is pretty much possible. And yeah, basically that was the intuition. Like we didn't know exactly what we were gonna expect. So
Also, I feel the simulation gives us a good
yeah.
like the like in the real world, we don't have the ground truth and everything, so it would be much tougher in the real world. But in the simulation, since we have the ground truth, the even the detection and the transformation becomes a little easier in general.
Yes. Yeah, we can try any other traffic scenario, or we can move in as well.
Why don't we go ahead and do the third test, and then we'll come back to, if we have time.
Okay, sure. Yeah, they will then, you can continue. I'll just press present. They will, are you muted?
Yeah, sorry about that. So I'll go over the demo 3. So the data which we gathered from trajectory and image processing systems will now then be used in the behavioral modeling, and then that behavioral model will then be replayed in the simulation to match the realistic scenario requirement. So for this demonstration, um, uh, we are showing that we are able to control 3 agents simultaneously in the simulation, and the agents which the model which we are using currently is learning by cheating. It's from the paper called Learning by Cheating, and that is designed for ego vehicle, and we have modified it to run it in a batch manner on a larger scale. So we propose that we will be able to achieve 10 FPS during this simulation, and we are able to achieve that around 9 to 11 frames per second. This number is dependent upon a few things, like we are running TeamViewer and Zoom on the same machine where we are running the demo. So I have a pre-recorded video after that where we have turned off everything, and I'll show that too. So uh, yeah, so the simulation will run somewhat in this fashion, where there will be 3 agents. We have marked that in blue, red, and black, and we can see that proposed the global path plans, and they are also reacting to the traffic lights as mentioned in the scenario here. So I'll quickly start the demo now. So I have started the Carla server, and I have prepared a demo view where we will be able to see all the whole view, where and also we can see the server FPS in the real time and number of vehicles on the top left corner. So I'll quickly add the agents one by one. So yeah, as you can see on the top right, bottom right, we can see one agent spawned. Bottom left, another one, and in the middle, the third one. Yeah, so in the server view, we can see current frame rate is around 7.3, 7.5. And so this will quickly reduce when we reduce the complexity. I have enabled agent debug view on the left. We can see what the agent sees and receives as input. On the green small rectangle, we can see the bird's eye view where all the lanes, all the traffic lines, and the other vehicles are detected for each agent. And these things are fed as an input to the agent, and then this simulation goes on. So in the next run, I will disable this agent view, and we will be able to see the FPS going up. I'll wait for the demo, this agent view to be completed. Yeah. So
from practical perspective, what is the significance of the number of frames?
so at the end of the day, this will be used for ego vehicle to be tested upon, and this will determine how quickly you can run one simulation to get your result. So
I see.
FPS, yeah.
Okay.
If you add a fourth one at this point, does it push it down significantly further?
Yeah, it'll push it down quite well.
How many agents are you guys hoping to be able to run in your ultimate tests?
I think in the ultimate test, we will try to focus on scenario type behaviors where at an intersection specifically how negotiations happen, how vehicle interact, and so we hope that we won't need more than 3 to 4 agents, but we are yet to plan how exactly that will flow through. And now I'll play the video where we are able to achieve 10 to 11 FPS. So this is without zoom and TeamViewer access and without the agent debug view. And yeah, here we can see the frame rate going up to 10, 10.4, 10.96 on the left corner. So with this, we are at the end of the demo. We can go over to any other part if you
Just one quick question on this, and then we could look at maybe some of the other, changing some of the parameters. Let's see, do you guys, I'm just curious if you've at least qualitatively seen a strong difference between how the agents that you've taught via learn from cheating behave versus the default behavior of the Carla cars?
So at the so the autopilot, so the default agents are called autopilot, and in a way the agents were trained on using the autopilot agents behaviors. So the training samples were taken from autopilot, like handcrafted autopilot agents, where they had put a few more restrictions on the behavior. So at the end, when we see the pre-trained model which we ran,
Yep.
they both behave almost the similar way, but in the following sem we will be taking human data using the steering wheel system which we got, and so that will be an interesting point where we will be able to see how human behavior gets translated to these agents.
Okay, so your goal is to capture the human behavior, and the hope is that that'll give you something different. Otherwise, there wouldn't be too much point in spending all this effort learning just to do the same thing, or more or less the same as the autopilot.
Yeah, the idea here was to set up the whole end-to-end pipeline, and then next,
okay, great. Dimi or TAs, did you guys want to look at any of the other scenarios?
I had a question about, sorry, I had a question about how you compute the multi-object tracking precision value. So usually for 3D objects, you do not have a percentage for Morley, right? RMSD value. The percentage only shows up when you have 2D object tracking where the ground truth and the detected box overlaps, and that's how you compute the precision. So how did you guys translate the RMSD values to percentage? over here?
Yes. So we set the threshold when we'll compute for under which we say whether the association was correct or not as 100. So we looked into the MOT benchmark, MOT challenge. So they also produce results in percentages of MOTP rather than the average deviation. And so the rationale how it is done is, so like you look at the threshold for under which you say a particular association is correct. For us, it was 100. So given the average MOTP, we are subtracting that from 100 and dividing it by 100. And that is how we're computing the percentages.
So basically, like this division by 100 would depend upon that confidence threshold, where which we say the association is correct from the ground truth. And let's say if this was around 20, then we would be basically subtracting it from 20, like 20 minus mod p, and then dividing it by 100, and then it will give it a percentage view.
Yeah, dividing by 20. Yeah.
Yeah.
Okay. Is that 20 meters?
So for us
Pixels.
currently it's in pixels, but
Okay.
yeah, it depends like which view you are looking into. So we are forward thinking to do it this on the Carla map itself instead of an image, static image, and in that case we would be transforming this to meters instead of pixels.
Okay.
Yeah.
Do you guys have, now it seems like your percentages are good for the various things you've achieved, but do you have any desired improvement or failure cases that you know that you can do better on?
Yeah, for at least for tracking, I can say like we did ran this on a real video as well, like without the metrics for sure. And we thought like currently our model does not includes constraints on the, like it's not a like a bicycle model. It's a constant velocity model, but it doesn't has this steering idea into that. And our next target is to, in order to make the trajectory smooth, so currently the trajectories can be a little bit jittery. So in order to make that smooth, we have to integrate a sort of a kinematic bicycle model into our tracking pipeline.
I see. Okay.
Yeah, for other systems, I think.
Yeah, for detection, I'm not sure if we would I don't think we'll work on improving. Like if we can, then maybe in the encore we can use the time for possibly extracting data from Carla during the demo, so that we have some very unknown scenario.
Yeah.
Does that sound plausible?
You asking me or are you asking your team?
To you. I mean, can we skip the first demo if it's okay?
Yeah, I think in general, whatever you guys can think of that doesn't involve just rehashing what we already saw this week, next week, that would be great. I think you guys did a good job of adding variability and scenarios, but we could spend a little bit more time maybe looking, I don't know, possibly prepare some more scenarios, prepare the 5 maybe ones, and we could spend some more time next time looking at how those work.
Okay.
Yeah,
Sure. Yeah.
Okay.
Okay.
I think we have about 30 seconds left. Any last stuff from anybody?
So I was just looking at our previous reports and FPS that we achieved with Carla. It looks like we were getting around 50 to 60 FPS with the Unreal Engine. So maybe you should try running it directly from Unreal Engine to see if it increases your FPS.
Okay.
Okay, yeah, we can surely look into that.
Cool. Thanks.
Thanks a lot, guys. We'll move on to Team F now.
Thank you so much.
Thank you.
Hello?
Hello.
Can you guys hear me?
Yep.
Okay.